Leave that place. Damn it. Leave that place. So this time we are asked to calculate the specific weight, the mass density, specific gravity, and specific volume of oil having a volume of 4.5 meter cube and weight of 40 kilonewton. So we have the given data. Volume of oil is equal to 4.5 meter cube. The weight of oil is 40 kilonewton, which is 40 times 10 raised to 3 newton. The first one we ask to find is specific weight. Specific weight is weight over volume. So the weight is known, 40 times 10 raised to 3. The volume is 4.5. So 40 times 10 raised to 3 divided by 4.5. That will give us that value 8.889 times 10 raised to 3. Right. So the next, we are asked to find the mass density of oil, which is given to us the specific weight of oil over acceleration due to gravity. The weight is already calculated in the first example there, which is 8.889 times 10 raised to 3. Acceleration due to gravity is a constant value, which is 9.81. So if we substitute all the values there, we have 906.1 kilogram per meter cube. Then number 3, we are asked to find the specific gravity of oil. So we use specific weight of oil over specific weight of water. Specific weight of oil is being calculated as 8.889 times 10 raised to 3. Now, specific weight of water, we can calculate that by calculating the mass of that is 1,000 times 9.1. 1,000 times 9.81. So that gives us 9.81 times 10 raised to 3. So if we simplify that, it gives us 0.906. Then the final one we are asked to calculate is the specific volume. Specific volume is reciprocal of density. So the density in number 2 is 906.1. So if you find the reciprocal of that, that gives us 1.1 times 10 raised to minus 3. So we move on to relationship between pressure and depth. Now, suppose we add an object submerged in water with the top part touching the atmosphere. If we draw a free body diagram, as we can see there, the atmospheric pressure is on top of the object. Then the object is exerting a weight force downward, and then the water in which the object is submerged is also resisting the object from sinking or moving down with a force that we call buoyant force, so, or upthrust. So we have the three arrows, two of them pointing downward and one pointing upward. So if we apply Newton's first law to that diagram, the sum of the force acting downward is equal to the sum of the force acting upward. So the water force is equal to the atmospheric force and the weight force. Now, remember that pressure is equal to force over area. So now we are dealing with force. And what we should do is to make force the subject of the formula. And that makes F to become PA. So from this expression, if we make F the subject of the formula, F becomes PA. PA. So in place of force, we have 1, 2, 3 forces. In place of this, the forces will replace the forces with PA. So the first one, which is force of water, is represented with this. Force of atmospheric, we represent it with this. Remember that the pressure, atmospheric force will give us atmospheric pressure. That's why we have a subscript of 0 to indicate that this is atmospheric pressure. Then we have mg. Our mg is transformed to density, volume, acceleration due to gravity. Because density is equal to mass over volume. So mass is equal to density times volume. So we replace mass with this rho v and substitute into the expression. Now, we also want to replace volume with this AH. Volume in meter cube, area in meter square, height in meter. So volume can be replaced with area times height. So if we do that, you will notice that all the parameters along so if you consider what we have done, all the parameters as A, area. So we have area here, it cancels this, the area will cancel out. So if that happens, we have P is equal to P subscript 0 plus rho GH. This first P is called the absolute pressure. This second P is the atmospheric pressure. And this other term is also pressure term, which is called gauge pressure. Gauge pressure. So they are defined here. Now, pressure measuring devices. Barometer, manometer, or boarding tube are devices used to measure pressure. Barometer, manometer, and boarding tube are used to measure pressure. Barometer of two types. We have the 14 barometer, and then we have the aneroid barometer. Now, manometer. A manometer is a U-shaped tube partially filled with a liquid as shown in the figure. There you see two different pressures from the two legs of the manometer, because the manometer is a U-tube shape or U-shaped tube. So here, if you look at this U-shaped tube, at one end of the tube, you have pressure 1. At the other end of the tube, opening of the tube, you have pressure 2. So two different pressures are applied to the tube. Then there's a fluid in the U-tube from from the top of the fluid up, that is your H1 on the first arm, and then the top of the fluid to the top opening, that is your height 2 for the second arm. And we assume that we have at some here, let P naught be the pressure at some point of the tube at the bottom of the instance. That is the statement for this. Now, if we apply the previous equation in the previous slide here, where we have the sum of the pressure, absolute pressure is equal to atmospheric pressure plus the gauge pressure. If we apply that formula to each arm of the tube, we are going to have the formula expression you have there. So now, if we equate these two expressions, we are going to have P2 minus P1 will give us this formula, rho G H1 minus H2. So if tube 1 is left open to the atmosphere, that is, this is left open to the atmosphere, then the pressure here will be atmospheric pressure. You know, initially we said that these two pressures are not the same. They are different pressures applied to both sides. So if this part is open to the atmosphere, the pressure here becomes atmospheric pressure. So in our expression here, if we replace P1 with atmospheric pressure, we are going to have this expression, which is P2 equals atmospheric pressure plus rho G change in H, which is similar to the expression we had in this place. This is still relating, showing how pressure is related to depth. So here is an example. The question says, calculate the absolute pressure at an ocean depth of 1,000 meters. Assume that the density of water is 1,000 kilogram per meter cube, and that the atmospheric pressure is given as 1.01 times 10 raised to 5 Pascal or Newton per meter squared. And B says, calculate the total force exerted on the outside of a 30 cm diameter circular submarine window at this depth. So coming back to A, we are given density of water, we are given atmospheric pressure, and then we are given the depth of the ocean. So we are asked to find absolute pressure. Absolute pressure, which is this, is equal to atmospheric pressure plus gauge pressure. So to calculate our gauge pressure, we have the density of water, then we have the height of the ocean, and then acceleration due to gravity, which is a constant value, 9.8. So if we substitute these values and simplify, we'll get 9.9 times 10 raised to 6 Newton per meter square. Now, the next question says we should find force, total force. Remember that pressure is equal to force over area. So force will be pressure times area. Pressure times area. Now, we know our pressure because we have calculated the pressure, which is the absolute pressure, 9.9 times 10 raised to 6. But we don't know our area. However, we have a clue on how to get our area because the submarine is circular and it's given, it has a window of diameter 30 cm. So since it's circular, the area of a circle will be adopted, which is pi r squared. Pi r squared. Now, r is equal to d over 2. D is diameter. So r squared becomes d squared over 4. So in the formula where we have A is equal to pi r squared, we are going to have pi d squared over 4. So if we convert 30 to meters, that will be 0.3 meters. 0.3 meters. Substitute that into this expression and simplify. Our area becomes 0.07. Force, therefore, will be pressure times area, which is 9.9 times 10 raised to 6 times 0.07. That gives us 6.93 times 10 raised to 5 Newton. So we'll move to the next slide. So here we are asked to calculate the density of oil. The question says a U pipe is initially filled with water on one side and oil on the other side, as shown in the figure below. The density of water is 1,000 kilogram per meter cube. If the height of the oil is 8 cm and the height of the water is 5 cm, what is the density of oil? Now, for this, we have rho GH1 will be equal to rho GH2. This is water, this is oil. This is oil. G is the same, acceleration due to gravity, so they cancel out. So this cancels out. So G cancels out. So we are left with rho of water, density of water, H of water, and then density of oil, and height of oil. So, but we have to find the density of oil. So that will be density of water over H of water and then H of oil. So this is 8/5. The unit cancels out. We'll be left with 8 divided by, okay. So that is 1,000 times 5 divided by 8. So that is 5,000 divided by 8. 5,000 divided by 8 is equal to 625. 625 density, which is kilogram per meter cube. Kilogram per meter cube. 265 kilogram per meter cube. So we move on to the next slide. Here, Pascal law. Pascal principle states that the pressure applied to a fluid in a closed container is transmitted equally to all points in the fluid and acts in all directions of the container. We can also state it as when external pressure is applied to an enclosed fluid, the pressure is transmitted undiminished or evenly to every point in the fluid and to the walls of its container. So this is a principle by that hydraulic press and lift. The principle applied to hydraulic press and lift or elevator, lift or elevator. So according to this principle, if I apply a force to this system, apply a force, this is a closed system. So if I have applied a force to this, in this direction, the pressure I apply, remember that pressure is force over area. So I'm applying force to this area. That pressure will go through this part and be transmitted equally. The pressure that is coming down here is the same pressure that will get to this point. That is according to Pascal principle. The pressure will not be diminished. The pressure will be evenly distributed across all the entire part in all directions of this closed system. So by that principle, we can come up with an expression. Since pressure in one arm is equal to pressure in the other arm, we have P1 is equal to P2, which is equal to F1 over A1 is equal to F2 over A2, because pressure is equal to force over area. So here is an example. The hydraulic lift has a large cross-section and a small cross-section. Large cross-sectional area is 20 times the small cross-sectional area. If on the small cross-section is given an input force of 25 Newton, determine the output force. So remember that P1 is equal to P2. P1 is equal to P2. Now the large cross-section has, and that is the small cross-section A1 is equal to A, that is the area. Large cross-sectional area A2 is equal to 20A, or 20 times small cross-sectional area. Then the input force in the small cross-sectional area is 25. The output force, which is at the large cross-sectional area, is F2. This is what we are asked to find. So by these details, we can write our expression as F2 is equal to F1 A2 over A1. So F1 is 25, A2 is 20A, and A1 is A. We have defined them. So A cancels A, we are left with 25 times 20, which is 500 newtons. So the force at the large section is 500 newton. Now we move on to buoyancy. When an object is immersed partially or fully in a fluid, such as a liquid, it is buoyed upward by a force called the buoyant force. Buoyant force. Buoyant force is also referred to as upthrust. It's a resisting force. Whenever an object is immersed in a fluid, the fluid will exert upward force on that object, trying to restrict the object from sinking down into the fluid. So the fluid will exert upward force. That is what we call the buoyant force. Now, when an object is placed in fluid, it displaces a certain amount of fluid. If the object is completely submerged, the volume of the object is equal to the volume of the fluid displaced. So this, you can try it out at home. If you have a bucket of water, not full to the brim. Now, if you take, let's say you want to wash your clothes. If you take some of your clothes and try to dip it inside, you will discover that the water level will rise. The water level will rise from its original level. So the difference from the original level and to the point where it is, the difference in volume is equal to the volume of the object or your clothes that you try to immerse inside or soak inside that water. So that is what buoyancy is telling us. So Archimedes' principle was taken from buoyancy. So it states that when a body is partially or wholly immersed in a fluid, it will experience an upthrust or upward force or buoyant force equal to the weight of the fluid displaced by it. And the upthrust acts through the center of gravity of the liquid displaced. That's Archimedes' principle. In a very brief statement, here, the one highlighted here, it can be stated as an object. An object is boiled up by a force equal to the weight of the fluid displaced. So if we measure, look at the figure here, if we measure this object in air, it gives us 7 pounds. 7 pounds. Now, by the time we dip this object inside this water, still measuring it, we notice that the weight of the object in water has reduced to 4, whereas part of the fluid has poured out from this part and taken in a bowl. So if we measure the volume of the water displaced and add to the weight of the fluid, that the weight of the fluid in the water, it gives us the weight of the fluid before it was immersed in the water. So by Archimedes' principle, upthrust or buoyant force is equal to weight of liquid displaced. The buoyant force is given as F subscript B. The weight of the fluid, weight is mg, is given as this. Now, m is replaced with density volume. So we put this here. Remember that weight or buoyant force is also mg. Remember also from our definition or from the statement that the volume of the object is equal to the volume of fluid displaced. So we can write that the volume of the object is equal to the volume of the fluid displaced. Volume of the fluid displaced. Here, we can replace this with mg, and then m with rho v, rho vg. So here we have the volume density acceleration due to gravity due to the fluid. Here we have volume density acceleration due to gravity due to the object. So the density are the same because we are talking of density of the fluid. So the density cancels out. Then acceleration due to gravity cancels out. We are left with the volume of the object and the volume of the fluid. So volume of object is equal to volume of fluid. Now, law of flotation. Flotation can be defined as the tendency of an object to rise up to the upper levels of a fluid or to stay on the surface of the fluid. Hence, the law of flotation states that a body will float in a liquid if the weight of the liquid displaced by the immersed part of the body equals the weight of the body. Or a floating body displaces its own weight of fluid in which it floats. So buoyancy, Archimedes' principle, and law of flotation, they are very, very close. It's just like a progression. So from this principle, from this law of flotation, there are 3 points that we should note. The first one is an object will float in a fluid if the average density of the object is less than the density of the fluid. which is a common sense. If I take a piece of paper and throw it on the water surface, so of course, we know that the paper has a light weight compared to the water. So the paper will float. That is the first point. Now, the second point says an object will sink in a fluid if the average density of the object is greater than the density of the fluid. So that is why stone will sink in water, because they have density greater than the density of water. Now, the third point is an object will be in equilibrium at any submerged level in a fluid if the object density of if the average density of the object is equal to the average density of the fluid. So if I have an object that has the same density as a fluid, has a density equal to the density of a fluid, that object will also float on the surface of the water. If the density of the object is less than the fluid, the density will float. If the density of the object is equal to the density of the fluid, the object will float. But if the density of the object is more than the density of the fluid, the object will sink. Now the question is, unfortunately, I can't hear you. The question is, the measure to which point 1 and point 3 will float will be different. For point 1, the point 1, which is object density less than fluid density, the object will just be on the surface of the fluid. No part of the object will be submerged. It will just be on the surface. And then point 2, that is the second one, where object density is equal to the fluid density. In that case, the object will submerge to an extent. Part of the object will be at the surface, part of the object will be in the water. That is point 3. But point 2, if the object density is greater than the fluid density, the object will completely be submerged, that is, sink in the fluid. So note the difference between these 3. Here we have a question. A cube of wood floating in water supports a 300-gram mass at the center of its top face. When the mass is removed, the cube rises by 3 cm. Determine the volume of the cube. So just imagine this. You place a wood on top of the water, then now place a stone on that wood. You will notice that the wood will go inside the water, submerge in the water. And if you now remove the stone, you will notice that the wood will float, will come up. The submerged part of the wood will come to the surface of the water. So we are asked to find the volume of the cube. So here, the volume of the cube, V is equal to L cube. When the cube rises by H is 3 cm, and then the density of water in gram is 1 gram per cm cube. The mass removed is 300 grams. So the volume displaced will be mass over density, which is 300 cm cube. So volume displaced is equal to area times H. Area is L square. H is height. So we need to find L2 because we already know volume displaced, which is 300. We know the height, which is 3. We know the height, which is 3. We know the volume displaced. So we can find the area, which is 300 divided by 3. So that gives us 100. L square is equal to 100. So L will be 10. So since we are asked to find the volume of the cube, we have now known the value of L. L is equal to 10 cm. If L is 10 cm, that is each part of the cube. Each part of the cube is 10 cm. It's 10 cm. So cube will be L cube. So that will be 10 raised to 3 cm cube. That is 1,000. I think our time is up. So we have other examples. I'm going to send the slide to you like last week. Now, you need to subscribe. Just click that subscribe button. That is all you need to do. Just click the subscribe button. Once you click the subscribe button, you have subscribed so that subsequent classes, you will get the alert. Immediately we come online, you will know without waiting for link to be sent to you. So click the subscribe button.